Okay, so you're probably surprised to see this say nuclear because we've been talking about how to make cars more efficient. We left off with stop and go driving, and normally the thing to do next would be to start taking a look at heating and cooling. However, we're going to have someone come and talk to us about nuclear a week from Wednesday. Now, a week from today, I'm going to be out of town, so there won't be any class. And we'll make that up by, don't forget, you're going to go see Dan Jurgen, the guy who wrote The Quest, on April 2nd. So that'll count for that class. And then this Wednesday, we're having someone from, I don't know if you saw on OSU Today or whatever the student version is at, the guys in chemical engineering made a big breakthrough in clean coal and chemical looping combustion. So someone from that lab is going to come and talk to us on Wednesday. So for me to tell you about nuclear before the nuclear guy gets here and sort of pave the ground, I had to do that today. That's why we're doing things out of order. So today is nuclear day. And the question is nuclear a source of green energy or not? We're going to talk about that. Last class, I just said all this. Okay, so Wednesday, March 20th, clean coal. Monday, March 25th, no in-person class. Makeup goes, so I guess I don't have to record a class either. So for you in-person people, don't show up. Makeup for that is to see Dan Jurgen on April 2nd, and then 27th we'll have Richard Denning from Nuclear Engineering. He's from Nuclear Engineering. He'll come and talk to us. So today I wanted to give you a little background on nuclear, and then we'll see what he says. So what's the difference between sustainable energy and renewable energy? So renewable would be, you can renew it, but sustainable means that you can live on it indefinitely or for some period of time that you specify. So we can say such and such an energy source is sustainable. We can sustain using oil for 20 years or 40 years, whatever it is. How long can we use nuclear? If we think it's long enough, maybe we would call that sustainable. But it's not renewable because once you use up the uranium, it's gone. So is it sustainable? That's what we're going to talk about today. Is it green? That's a matter of opinion. Okay? There's two different kinds of nuclear reactions. So the usual one that we use in our reactors is fission. You take a big atom and you split it up into smaller atoms, and what comes out of that is energy and lots of it. Fusion is what happens in the sun, where you take small atoms like deuterium and tritium and you combine them, and what comes out of that is energy and lots of it. The key here is lots of it. All right, in fact, nuclear energy from atoms in fusion or fission is 1,000,000 times greater than atoms from chemical reactions. So we're talking serious energy here. So that means that to get the same amount of energy, you actually need 1,000,000 times fewer atoms. So the volume of the fuel is a lot less. So the fuel is small, and the waste is small. I'm not saying I want the waste in my kitchen, but it's physically small. So why nuclear? Well, it's a different source of energy. We have uranium, thorium. This is as opposed to sunshine and wind and so forth. It doesn't create much CO2. There is CO2 in the construction of the fuel plants or the reactors, the trucks that transport the uranium back and forth, and mining and so forth, but we're not burning fuel to create the energy in this case, so there's no CO2 with that. And there's very little waste. Again, I'm going to stress volume-wise. So it's a small volume, but we still have to deal with it. So those are good reasons to use nuclear, but why would we not use nuclear? One is, does sustainable use produce enough energy, and for how long? So how long do we want to be on the planet, or how long do we want to care about? The waste is toxic for a very long time, as you know, thousands and thousands of years. And the technology isn't proven, at least fusion. So we don't know how to do fusion well, but we know how to do fission. So those are some arguments against nuclear. The key one that Joe Public worries about is the waste, I think. Well, that and the risk of accidents. What happened? Nothing. All right, so now let's think about this. The mass of fossil fuels, let's say the average Brit consumes 16 kilograms of fuel. So that's about 4 kilograms of coal, 4 kilograms of oil, and 4 kilograms of natural gas. So that's about the same weight as 7 gallons of milk, for comparison. Nuclear fuel, to create the same amount of energy, is about 2 grams. So that would be a cube about a 64th of an inch on a side, or the side of a grain of salt. A grain of salt in nuclear, that's volume, produces the same amount of energy by weight as the 7 gallons, of milk. That's pretty impressive. Did I mention it's a million times more energy than in chemical reactions? And then the waste, again, size of a grain of salt. Here's a grain of salt on the head of a pin. And that's per person in the UK per day. But it's radioactive waste, so you can't just wash it down the sink or anything. You still have to deal with it. But it's incredible, the volume. All right, so here's a poll. The world has about 5 megatons of uranium in the ground. Depends who you ask. Our book says that you can get 1 gigawatt year of energy from 162 tons of uranium. So how many kilowatt hours per person per day can fission support sustainably? And sustainably depends on how long do you want to be sustainable for. Now, I was working on this the other day, and I was doing this calculation, and I had to spend 15 minutes getting the calculation to come out right. So it's not like I think you're going to do this in your head, so we'll just guess. How many people think 100? Okay, we got some guesses. How many people think 10? How many people think 1? Someone was looking in, I didn't think needed help. How many people think 0.1? We don't have any idea. Let's do the calculation. A gigawatt year divided by 162 tons is 54 mega kilowatt hours per ton. So the answer is C or D, depending on the precision. Let's go back. C or D, this is how many kilowatt hours per person per day can fission support sustainably. This is so-called once-through. So I predict that Dr. Denning is going to tell us about once-through reactors and breeder reactors. Once-through means you take the fuel and you get the energy out of it and you put away the waste. A fast breeder, they actually can reuse the fuel, and they convert the uranium to plutonium, which then can provide more fuel, so they get a 60x increase in efficiency. If you do that, then that's more than 30 kilowatt hours per day per person. For some length of time that isn't specified here. How long is sustainable? Fast breeders are only partially proven, and it'll be interesting to hear Dr. Denning come and talk to us. I hope he'll tell us about that. If not, we'll ask him. So currently, we get about 20% of our energy from nuclear. So here is U.S. electricity generation. This is coal, you're not surprised. This is natural gas, 25%. Nuclear, 19.25%, and then your renewables. This is petroleum. Because this is to produce electricity, right, not our total energy use. And we have about 104 nuclear plants in the United States. This is where they all are. I don't know what the colors signify. I was trying to guess. They're sorted by regions. Maybe they're different nuclear authorities. Few reactors have been built in the last 30 years. New government policies. They're expected, about 4 to 6 new plants were expected to come online by 2020. There's some applications to build new plants, but then after Fukushima, people are going, well, I don't know. Recent lower gas prices, so the price of natural gas has been coming down. Maybe it's not as cost effective to make nuclear after all. And we're going to take a look at the price of uranium shortly. Do we have much uranium? Actually, we're 6th in the world for known uranium resources. These are ones that we already know, they're in the ground, someone has laid a hand on them and found them. And we mined a lot of uranium in the 1950s. But then the price for uranium prices were going down. Decreased from 250 to fewer than 10 mines, prices were going down. Oh, I know what it is. The price of the uranium was going down, so it wasn't worth it to mine it. It was more cost to mine it than you could get selling it, so it decreased. Now, then the price started going up, so people started looking at reopening some mines. Now, here is, well, first let me talk about this. Our sources of uranium are not the highest, evidently, and we import 90% of our uranium, 95% of our uranium from Canada, Australia, and Russia. Here is a plot of US dollars per pound of yellow cake, this is uranium, from 1948, and this blue is in actual dollars. It normalized to current currency, and this is the actual, no, it's the other way around. constant $2,007 here, and that was the cost at the time. So there was this big peak in 1978, so it looked like a good idea to mine uranium, because you could sell it and get some money for it, and then it went back down again. And then recently, shot up again. So people said, whoa, maybe it's worth it. More recent data, this starts at 1974 and goes up to 2010. So here's when 3 Mile Isle happened. Here's when Chernobyl happened. This blue one is oil, by the way. So this is dollars per pound of yellow cake, and this is dollars per barrel of oil. And then here's where that was shooting up that I showed you on the last graph. And everyone got all fired up, and then whoa, went back down again, and Fukushima happened. Here's uranium mining. These are the largest producing uranium mines in 2011. And this one is in Canada. Tons of uranium, 7,600 and something, 14% of the world's. Olympic Dam in Australia, 3,000 and change. Arlit in Niger. All right, I can't pronounce that, but it's in Kazakhstan. Here's Australia. Here's one in Russia. Here's some hard to pronounce places. Namibia, Kazakhstan. Kazakhstan's loaded with uranium, evidently. And uranium is actually more abundant than gold. I was surprised to learn this. Gold, silver, and what was the other one? Mercury. Just radioactive. Oh. So here is a chart that shows a process, the mining. So you mine the ore, and there's a couple of ways to mine it. We'll talk a little bit about that. Then after you get the ore, then you mill it and refine it into yellow cake. That's the actual fuel. The yellow cake goes over to a conversion plant where it's converted to uranium hexafluoride by fluorination, and we'll mention that shortly. Then it gets put in steel cylinders and it gets enriched in an enrichment plant. And again, I'll talk about all these things. I'm just trying to show the big picture. This says, I can't read that. Something steel cylinders, LEU, some steel cylinders, fuel fabrication. There's Navy fuels and depleted uranium, so there's possibility of getting depleted uranium and using that for fuel, enrich that. Here's depleted UF, storage yards, depleted. So people are talking about maybe getting depleted stuff and enriching it and using it as fuel again. Once they get the fuel fabricated after the enrichment, then it gets made into fuel rods and made into a reactor and burned, so to speak. And then you have spent fuel that you have to figure out what to do with. So mining, there's two different ways to mine uranium, evidently, and one is open pit. So if this is a Navajo and this is on your reservation, you're not real happy about this. Big hole in the ground. It's bad for the environment. You chop up the rock and you cart it away to a processing plant. The other way is underground using in situ leaching. It's basically fracking. So they pump fluids down here under the ground and suck out the ore. They leach it and then they pump it back in, and radon lives here. So some people say that's better for the environment, but the jury's out about fracking. So who knows what it does to the geology, so forth, but it doesn't look as bad from the top. This says potable water well. Ooh, that doesn't look too good. Ore milling. So if the ore is mined in an open pit, then you have to mill the stuff to make yellow cake. Yellow cake is U3O8, and there's a chemical process. So they crush the ore and then they chemically leach out the uranium and combine it with oxygen to get this, as opposed to the in situ leaching where they do this chemical reaction underground where you can't see it. Yellow cake. Not delicious. Then you got to convert the yellow cake to uranium hexafluoride, which I understand is a gas. There's only one plant in the United States that does this right now that I know of, or that I could find about. Honeywell Metropolis Works in southern Illinois. So here's that picture again, and we are at the conversion. So we did the refining. Here's the conversion. And then you have to enrich it. So it turns out that only, when you dig uranium out of the ground, only 0.7% of that uranium is fissile. So fissile means it's U-235 isotope as opposed to U-238, which is more common. So you can't do fission with this. So you have to enrich it to get more U-235. Fortunately, these two isotopes are slightly different in mass, so this is where the centrifuges come in. They actually can spin these at crazy speeds, and the heavier stuff goes out farther, and they can separate them. So, or you can use diffusion. And to get fuel, you need 3 to 5% U-235. So you started with 0.7% naturally occurring, 3 to 5% is good enough for fuel. So that's how it's enriched. And then you have this stuff left over. Okay, so enrichment continued, you end up with enriched uranium, and the other stuff is the depleted uranium, because you preferentially move the 235 into the stuff you're going to use. So the depleted uranium, people use it for bullets and missiles, because it's denser than lead, but you also use it for armor, and armor penetrating ammunition, and also for armor. And it is radioactive. It has gamma rays, but it's not as radioactive as a fuel. Here's a bullet made out of depleted uranium. This is a tactical M900, whatever that means. This says primer, this says steel case, tracer, aluminum fin, propellant, aluminum, depleted uranium penetrator. That's this thing here. I had no idea. Did you guys know this? That they make stuff out of that? I guess I don't get out much. I thought it was pretty interesting. And so, what if you kept enriching it? So you need 3 to 5% to make fuel here. If you keep enriching it, this is U-235 content, 3 to 5 is over here. Research reactor, 20%. Okay, you have to work harder to get it enriched. 90% to build a weapon. This says effort, SWU per ton of U feed. I have no idea what that means. That's a very impressive graph. So after the enrichment, you increase it to 235 to make the stuff that's going to be fuel, and so the rest is depleted. Excuse me. So let's say start with 1,000 grams of natural uranium. You enrich to 5%, you get 85 kilograms of fuel, and then you have 900 kilograms left over, depleted uranium, and the concentration is about 0.3%. Excuse me. Guess I'm not over this cold yet. So you can deconvert it, bind it up again in the UF6. Or you can store it, depleted uranium typically stored in 14-ton cylinders, stored at the enrichment factory, because you don't want to be driving this stuff around all over the country. Here's a new cylinder. Here's a not so new cylinder. You can also sell it for use as counterweights for elevators and cranes and shielding, because depleted uranium absorbs gamma rays, so that's a good thing. You can dispose of it at commercial sites. The U.S. is currently storing 700,000 metric tons. Look where they are. Oh, in our backyard. Portsmouth, Ohio, I didn't know that. Uranium mining in the U.S., although we don't mine a lot of it, evidently what we do mine is mostly in situ leaching. So it's hydraulic fracturing, pump a solvent down the well pipe, sulfuric acid or sodium bicarbonate, pump the dissolved ore up to the surface. So the nice thing is you don't have as much radiation exposure to the employees, because the stuff's below the ground mostly. Lower cost, there's no tailings. Tailings are the stuff when you mine, leaving big piles laying around. But you could contaminate the groundwater. Again, we don't know what's happening to the host rock. The waste sludge that's produced, you can't restore the leach zone to natural conditions. So there's pluses and minuses. Here's uranium mines in the United States. Crow Butte in Nebraska, annual production 363 tons. Much smaller scale than what we saw in Canada and Kazakhstan. Smith Ranch Highland, this is near Wyoming. This one's in Texas. This one's also in Texas. And this is annual production tons of ore, and this is tons of uranium, so there's a difference there. And a type of mine, in situ leaching, that's what that stands for. And the interesting thing is, there's no uranium mines around here that I know of, but we do have a lot of radon. So we have radioactivity in our rocks. But I don't know enough about it to understand why that is. So question is how much uranium is there in the world? There's known conventional resources. So there's different ways to estimate this. So you can say, well, how much uranium is there? Well, there's some that we know is there. Known conventional resources means someone has looked at it and said, yep, there's that uranium rock right there, and we know it exists, and it's inexpensive to get. So there's two kinds of reasonably assured resources. This accounts for the losses in the mines of processing and reported in 3 categories according to cost. So for example, they'll say, well, how much could you get if it was if uranium costs less than 40, or you could sell it for less than $40 a kilogram. Well, if it was, you could sell it for less than $80 a kilogram. Now there's more that you can get at for that price. Or for 120, then there's even more. So it depends on the pricing. And estimated additional resource category 1, I think maybe it's on the next slide. No. Undiscovered conventional resource. So I like this. It says, oh, this is, well, we believe it exists because we know what the geology is like, and we know what kind of geology produces uranium-producing rocks, and we know there's, places like Colorado, Wyoming have uranium, so probably there's more uranium out there that we haven't actually laid eyes on. If you want to believe it exists, then you can put that into your calculations for how sustainable is uranium. If they exist, then we would be able to get uranium using conventional mining techniques, because this is based on believing that they're there where there's other uranium based on the same geology. So if you're trying to estimate how much uranium do we have left in the world, you could say, I believe we have this much, I know we have this much because we've seen it, or you could go with this number, this is how much I believe is probably out there, so we can count on it. And then there's secondary sources like previously mined uranium. Well, if you want to count the stuff that we're storing that we might want to reprocess stored by governments or by companies or held by the military, depleted uranium that's stockpiled if you want to reuse it, those would be considered secondary sources. So some people would like to count those in their estimates. And then there's unconventional sources. So it turns out that uranium is also present in small amounts in phosphate deposits. We know how to get the uranium out of phosphate deposits, but it's expensive to do it. So the question is, if you want to count this in the amount of total uranium attainable, question how much you're going to pay for it. Or seawater. Now it turns out, this is weird, seawater contains a lot of uranium. Okay, it doesn't contain a lot of uranium, but there's a lot of seawater, so it adds up to a lot of uranium. The problem is we don't really know how to get it out of there. Yes?
Do you know how much uranium is in a certain volume of...
Well, I don't remember, but I think it's in my slide somewhere.
Okay.
Let's see. If it isn't, you can sue me. So, how much uranium is there? Here's known recoverable resources. So this is the first category. 4.7 megatons in the ground, known recoverable. How long would that last? Depends. So here's million tons of uranium. Here's a bunch of countries that have a bunch of million tons of uranium. Here's a world total conventional reserves in the ground, 4.7. Then phosphate deposits, another 22. That's huge compared to the 5, but expensive to get. And then in the seawater, is this your question? 4,500. Boatloads, but we don't know how to get it. People are working on it. How long will uranium supplies last? So this is where it depends on who you talk to and what their agenda is. Uranium reserves, U.S. uranium reserves now about 20 to 23 years worth by one estimate. So this is from CNEAF, Nuclear Page Reserves, whoever they are. European Commission says it'll last 42 years, the world's supply, at the current rate of use. Or 100 years. If you're this other organization. So it depends on how you do the calculations. And others say there's even more than that, and it will never run out. Depends what you count, and also depends on, well, we'll get to it. So here's another analysis. Here's the little square in the corner is reserves in current mines. And I don't know what the units are here. This came from OECD-NEA.org, whoever they are. The 80 is the known economic reserves, known to exist and relatively inexpensive to mine. Conventional, this green, conventional undiscovered resources, believed to exist but not discovered yet, that would be the 300. And then total ore resources at 2004 prices is this 1500 years. Oh, and these are years over there. And unconventional resources is who knows, e.g. and seawater. So, again, depending on what we don't know is, yes?
You can finish your sentence.
What we don't know is, are they accounting for population increasing? Are they accounting for the rate of energy increasing? Or are they just saying, we have 7 million people now, we're going to continue to use this much energy, how long will this stuff last? So we don't know that either. What was your comment on me?
We're also, I don't know if they're taking into account next generation reactors as well.
Right.
That could take what we currently have and extend the lives significantly.
Yeah. For example, if the breeder reactor is 60 times more efficient because it makes more fuel, are they using that here? Who knows? So that's why these numbers are all over the map when people say is it sustainable. Yeah.
What are the 20, 80, and 30 units?
Years. How many years do they think it will last?
So how can they go from what we believe exists but haven't discovered yet is 300, add that to, so we got 400 and it turns into 1500 years somehow? Unless I'm like reading this graph wrong.
I don't know. Reserves and combined, known economic reserves, conventional undiscovered resources, and then total ore resources at 2004 prices. $2004 prices was pretty high. So that must be because they figured that you could get more out. It would be worth your while to mine it at those prices. But we don't know what prices they're considering here.
Okay.
So who knows? But it's just, people, like I say, people give you all kinds of numbers and they can pull them out of their hat. Cost of uranium again, I just want to stress this as a factor. As the price of uranium increases, the value of mining it increases. But the corresponding cost of the energy is also going to increase. This is the same plot we showed before. So we could get to the point where we're willing to pay mega high prices to get the uranium, in which case, yeah, we would have more uranium and we could go longer. I think whatever we do in the future, energy is going to get more expensive, and we're either going to suck it up and pay it, or we're going to finally learn to conserve. Uranium might be there, but is it cost effective to get it? If the price is below $130 per kilogram, it's only worth it to recover about 1/1000th of the amount in seawater. If the price goes up, it might be worth going after the stuff in the phosphate deposits. Again, here's the numbers for those. We used to mine the stuff in the phosphate deposits, but it was expensive and it wasn't cost effective. Again, the uranium in the seawater, we don't have the technology to get it. And I'm going to talk about these a little bit. So here's McKay's estimates. He says let's do ore-based uranium and then include seawater so we can compare the two numbers. So we'll consider the two methods, the once-through reactor and the breeder reactor. So the once-through reactor works like this. Uranium atom absorbs a neutron, so you need to have a source of neutrons. The neutron changes at 235 to 236. Then that decays, one atom of that decays and produces 200 mega electron volts. Wow. So I'm a semiconductor guy. I think in terms of milli-electron volts, this is incredible. Then it splits the atom into two atoms and give off neutrons. Neutrons are good because they create this reaction, so you have a source of neutrons there. They also create gamma rays, and then the atoms have kinetic energy, boom, right? So they collide with other atoms in the reactor, and that's where the heat comes from. So these things shoot apart, crash, generate energy, generate heat. Then the neutrons also have lots of energy, so you can collect the neutron energy and convert that to heat. And use some of them to keep the process going. But you got to be careful it doesn't run away. What would that be called? Nuclear meltdown, something like that. So the way the reactor works is they take the enriched uranium and they make it into these pellets, and then they form the pellets and pile them up into these rods. They're like tubes, and then they collect those rods into bundles, and it can overheat and melt, as we know. So to keep that from happening, to keep the reaction from getting out of control, you submerge it in circulating coolant water to keep it cool, transfer the heat to the water. And then you make the control rods. So in between, in this bundle of rods of fuel rods, there's these control rods that can absorb neutrons. So you pull the rods out and they don't absorb neutrons, and neutrons make the reaction go and it gets crazy. And then if you want to slow it down, you put the control rods in, they absorb the neutrons, and you don't have as much of a reaction. So that's how you control the rate of the reaction. Okay? Then the heat that you collect is used to generate steam. And you know the rest. Steam generates turbines, doesn't generate turbines, turns turbines, convert the thermal energy to mechanical energy to electrical energy. There's losses involved. But boy, with uranium, you have a lot of energy. How about the efficiency? To get a kilogram of nuclear fuel costs $1,300 to mine 8.9 kilograms at $146 per kilogram. $98 to convert 7.5 kilograms. $11.32 to enrich it, down to 7.3 kilograms. $240 per kilogram to make the fuel. So the total cost is $2,769. Doesn't include the cost of the plant, but it produces 360,000 kilowatt hours per kilogram. So the fuel cost works out to 77 cents, 0.77 cents per kilowatt hours.
It's basically free.
It's basically free, not including the cost of the plant.
Right.
I'm worried this might be $0.77. It might not be 0.77 cents. But it's still cheap. What do we pay for a kilowatt hour now? I don't remember.
Like 8 or 9 cents or something.
8 or 9 cents? Then this is probably right, because I think it works out that it's incredibly inexpensive.
Yeah.
And it's expensive. These numbers, this looks like a lot. It's the thing is how much energy it produces. It's out of control. So once through plants with ground uranium, a gigawatt plant uses 162 tons of uranium, or 54 megakilowatt hours per ton. We said that before. At 4.7 megatons in the world, that was one of the numbers we had before, divided among 600 mega people, that was in the world the last time that I made these slides, that works out to 0.55 kilowatt hours per day per person if it has to last 1,000 years. So one definition of sustainability is let it last 1,000 years, but then we'll have time to figure out some other way to do stuff, just like the sequester. When we had to make ourselves figure out a way to solve this problem, and then we didn't. So we have 700 mega people now, so if you can call that 0.47, a little bit less than half a kilowatt hour per day per person. That's the output of about 116 power stations, so that's about half of today's production. There may be more uranium out there, depends on how you estimate it and how you count it, so there's a lot of uncertainty. And this number here, for the 1,000 years, assumes that the population stays constant and our energy rate of consumption stays constant, which, what are the odds of that? All right, but what about the neutrons? Well, they're highly energetic, so they get slowed down. They're thermalized often by absorption in the coolant. Turns out that water can absorb neutrons. Slow thermal neutrons have a higher probability of splitting U-235, plutonium, these other two plutoniums, than they do 238. So that makes it possible to use lower grade fuel. And you have the neutrons. Fast neutrons, before slowing, can fission the 238 as well. So you end up producing more fissionable material that can also be burned if you use those hot electrons or hot neutrons. And I think I'm hoping Dr. Denning will talk about this. Now, a fast breeder reactor does that. So it uses those high energy neutrons and it produces more fuel. So it's called a breeder because it produces energy, but then those high energy neutrons, where'd they go? They're fast neutrons, can fission the background. This isn't the usual fissionable stuff as well, and that produces more fuel. So breeder reactors that make more fuel, 60 times more efficient than a once-through reactor. You can use depleted uranium for waste stockpiles as fuel. Here's a fast breeder reactor under construction in India, but I don't think these are really ready for prime time yet. If you use ground-based uranium in a fast breeder reactor, you can produce more like 30 kilowatt hours per day per person for 1,000 years, assuming the population doesn't change. that's based on known recoverable resources. These are ones that someone has laid eyes on. The book gives 33 kilowatt hours per day, but they use 600 people. I use 700 people, 700 billion people. And then what about ocean uranium? So the oceans have some uranium dissolved in it, but the ocean's huge. So there's lots and lots of uranium out there total. But extracting uranium from the water is unproven. So I'm going to show you a couple of approaches. Mostly ocean water is very deep and it cycles slowly, so the water from the bottom of the ocean takes a while to come up to the top. So maybe, since we can't get to all the water at any given time, maybe we could extract, here's a number, 280,000 tons per year, if we knew how.
What was our current production? Tons per year?
US?
Worldwide.
Oh, 4.7 megatons. Oh, that's how much we think is,
Yeah.
should go to this.
How much are we currently producing?
I think this is reserves here, or this is, yeah, world total convention. I don't know what we're producing. What are we producing? Did I have it anywhere in here? How about here? This is 2011.
That's a pretty good. So that's 52%. So
Yeah,
Right around
and that that's 28,000 tons of uranium. Now, what were we talking about?
you said 280 or something.
Okay, so it is a significant number. 280,000. Good question. If we knew how. So here's one trial. These guys are using it's called a uranium-specific non-woven fabric as an absorbent. So basically it's a big wad of polymer, and this made as a braid, and they put it in the ocean and they let it soak there, and it absorbs uranium. 350 kilograms of fabric recovered 1 kilogram of yellow cake after 240 days. So the better part of a year. 350 kilograms of fabric got 1 kilogram of uranium. Cost estimate about $300 per kilogram, so it's expensive. I'm going to show you this figure on the next slide so you can look at the details because it's kind of small. The price, the last time I taught this course, which is in 2010, uranium was $123 per kilogram. I looked it up for last month and it was 42. So this is not cost effective yet. But here's a picture of that slide. So it says the temperature effect of the seawater. It's a utilization of the braid adsorbent. Temperature effect of seawater 1.5 times. I don't know what that means. Geometrical effect of the absorbent 2 times. Absorption performance enhanced 3 times, I guess, over the basic material in the lab. And so here's the braid. Here's offshore mooring. Here's the yellow cake obtained from the seawater. Here's a little jar. This says absorbed of uranium, grams of uranium per kilogram of absorbent. So stack, here's one kind, stack absorbent looks like this, and then the braids are different. So with the braid, this particular paper was showing off the braids. They're using the same material, I think. It's just how you weave it. So this data here comes from this demonstration here.
Do they know how it affect? Like, what is the effect of uranium in an ocean? Do we have any idea?
It's been there since time began. So, I mean, even the rocks under our houses are slightly radioactive, so I don't know. I guess it's low enough it doesn't bother anybody.
Do we know the effect of removing it, though?
That's what I.
Oh, no,
Yeah.
interesting. Clearly we don't know the effect of removing
Oh, 'cause
it.
we can't do it yet. Yeah.
Yeah. Very interesting question. Good. Other methods I found out there, mutated green algae, 1973. Giant underwater sponges. Actually, this is just the polymer adsorbent method on a bigger scale, so they made sponges instead of braids. I think if you have sponges and you add them to radioactivity, you end up with cartoon characters. sponges that can talk and wear pants. Huh. So how much could we get from the sea? If you used a once-through reactor and you shared among 600 million people, it might be 7 kilowatt hours per day per person for 1,600 years. If you wanted to last at 1,600 years, and if the number of people stayed constant, it would require about 4 times as many reactors as exist now. So it's not the same change in infrastructure that we saw for adding windmills and solar, except for the part about figuring out how to get the uranium out of the ocean in the first place. And this is required 4 times as many reactors, but the volume of this absorbent is insane. We'll have a slide about that in a sec. So 7 kilowatt hours per day is not enough to get us off of fossil fuels, and it assumes that the reactors can recover the energy cost of getting the uranium out of the ocean in the first place. So let's go for broke. So let's use seawater uranium and fast breeder reactors. If you do that, now you can get 420 kilowatt hours per day per person for 1,600 years. And that would be sustainable. Oops. We don't have technology to remove the uranium from the seawater. Is it scalable? Oops, fast breeder reactors are not widespread. Are they scalable? We don't know yet. Are they dangerous? Don't know that either. But if you believe these plots, here is, the top is once through reactor, the bottom is fast breeder. This is mined uranium here, ocean uranium here, if you believe in it. River uranium, there's water in rivers too, so. This is why I think nobody knows for sure if uranium's the answer. Is a giant sponge scalable? So let's think about that. 350 kilograms of fiber. It collected 1.6 kilograms of yellow cake per year at that rate, whatever we saw for 240 days. The cross-sectional area of that fabric was 48 square meters. If you use it in a once-through reactor in a gigawatt station, you'd need 160,000 kilograms per year. So that's 200,000 times greater than the demo. And this is a picture that's labeled in another language that I don't know what it is. And here's wads of fabric hanging from a bridge or being moored underneath the water or underneath a plant here. Uranium sponge then you'd need 350,000 tons of the fabric, occupying 48 square meters, would weigh more than a reactor. But let's say you had that, and say it delivers 222 kilowatt hours per day per person. The 1 gigawatt reactor supplies 1 million people. Each person needs this tiny amount of uranium per year. That just kills me. And then to get that much uranium, each person needs 5 square meters of ocean. So I need someone out there with the rags collecting 5 square meters just to collect my uranium. Is that reasonable? Well, what was it, 5 square meters? We said I needed 10 square meters for solar to put on my house. That wouldn't supply all my energy needs. We now think that every person should have a 1-ton car and a dedicated parking place for it, yeah?
You said it was 5 square meters, not cube?
It was square meters.
How can you...
Of ocean.
Yeah.
Well, yeah.
How... Wouldn't we need to do that by volume, not by...
You'd think you would do it by volume.
Yeah, it can't be an infinitely small layer.
Unless
No, I thought it was a column whose
That'd be a lot.
projection on the surface, but you don't know how deep the ocean is, and so I'm not sure where that number comes from now that you say that. But, so McKay's argument, I believe this is McKay, was saying, is that absurd? Well, we already think everyone should have a car and a parking place for it, so maybe it's not that terrible. And then there's other stuff. So there's something called thorium, another element. There's 3 times as much thorium in the Earth's crust as there is uranium, but there isn't that much in seawater. It can be completely used up in a reactor. So the reactor, uranium only uses up 1% of natural uranium, but you still have radioactive waste, so don't get too happy. In the reactor, the thorium turns into an artificial uranium isotope 233, and that becomes a nuclear fuel. You still need neutrons from somewhere to cause the reaction. And then you can fission the fuel in situ or separate it from used nuclear fuel to make new fuel. So I don't know, people talk about thorium. Pros and cons. Pros, thorium is more abundant than uranium and it's more efficient, uses neutrons more efficiently. It has better physical properties like better heat conduction and a higher melting point, so it won't go to melt down as easily. I suppose that's good. But on the other hand, it's not fissile on its own. You have to add neutrons, so you need some other radioactive material to get it started. There's some technical difficulties involving its chemistry that are not specified here, but somebody knows about them, I guess, because they put them. Byproducts have long half-lives. That is true of uranium as well. But they do exist. So there were 6 in the U.S. They've all been closed now. The biggest one was in Colorado. It's this place here. It's now a gas plant. It burns natural gas. It was successful, but it had very expensive problems. And the only thorium reactor left in the world supposedly is in India. And it looks huge and scary. I don't know if those are the rods. The rods are that big. I don't know what that is. Then there's this idea of an energy amplifier proposed by this Nobel laureate back in the day. This would allow for long-lived transuranic elements, radioactive ones, and nuclear waste to be used that create energy and also shorter half-life wastes. The estimate was convert 6 million tons of thorium to 15,000 terawatt years. Wow. Or 40 kilowatt hours per day for 1,000 years. Once converted to electricity. So this guy said eventually 300 times more thorium will be extractable, reaching its potential 120 kilowatt hours per day per person for 60,000 years. Says so right here in my lab notebook. That's what I'm always telling my students. Must be true, I wrote it in my lab notebook. So writing it in your notebook and making it actually work in real life is not the same thing. Land use. So now we're back to England again. Suppose Britain builds new reactors. Even if they're not sustainable, they'll reduce the carbon dioxide for heating and transport, but is there room for them is his point. So he figures out the power per unit area of reactor, 1,000 watts per square meter. If you generate 22 kilowatt hours per day per person, that's about 55 gigawatts, which is what France produces. They use a lot of nuclear. Could be produced by 55 1 gigawatt stations. So the question is, how much room do they take up? Well, he'd put them along the coast so that you can have cooling from the ocean. Each one of those plants occupies a square kilometer, so they need about 0.02% of the land, about 500 times less land than wind to produce the same amount of power. He's suggesting you could put 2 every 100 kilometers and use about 2% of the available coastline. So is that something they could tolerate? And if they could find the uranium. And then there's the toxic waste. What's the cost of the cleanup? Well, this is the British Nuclear Decommissioning Authority has an annual budget of £2 billion for the next 5 years. The UK produced this much energy for the last 25 years from uranium, from nuclear. So the disposal part of the life cycle, 2.3 pence per kilowatt hour. And compared to the subsidy for wind, which is 7 pence per kilowatt hour, that's 11 cents for us. So, maybe the disposal is not so bad. You have to pay to do it, but comparing to subsidy for wind. Toxic waste, where are you going to store the spent fuel? The rods are hot for years after removed from the reactors. Usually they just store them at the reactor because you don't want to drive these things around and give people a chance to grab them. They have to keep them in water. The water keeps the rods cool, and it also absorbs radiation. So they circulate the water. They use the heat exchanger to remove the heat without mixing the water. And the pools are at the reactor. There's a reactor here on campus. It's over on West Campus. They have a neutron source. I don't know if it's a reactor. I think it's a reactor. And they also have a gamma cobalt rods that produce gamma rays. And they got a big giant pool. It's amazing because it's like 20 feet deep and it's clear. And the cobalt rods that produce the gammas, they glow blue. It's very cool. You go in there and you have to wear a radiation bag. But the nuclear thing, the thing that produces the neutrons, is not in the pool. It's around back. It's just a little, it looks like a brick oven almost. But I don't know what they do with it. Maybe Dr. Denning can tell us more about it. Some of the materials in the rods have short half-lives, like iodine, is 8 days. But others, like plutonium, 24,000 years, so that's bad. 10 years later, the radiation at 1 meter is 20,000 rems per hour. To give you an idea, if you got a 5,000 rem dose, you're dead. Unpleasantly dead. Other risks, the rods have to be kept separated to avoid a runaway nuclear chain reaction, so the rods have to be cooled for the same reason. If the cooling is interrupted for a prolonged period, the water can boil off. Gee, where did this happen recently? Resulting in radioactive elements being released in the atmosphere, which is very bad luck. The chance of fuel reaching criticality is very small. Neutron absorbers are used around the rods, so more materials to absorb that. And the rods are arranged in certain patterns to minimize the risk of them irradiating each other. Once the pool is full, you still don't want to be driving the stuff around, so now you start storing it above ground in these storage casks, again, usually at the reactor site. Fukushima. When the tsunami happened, reactor 4 is this one down here, had been defueled. 5 and 6 up here were in cold shutdown, so that only these 3 were still in operation. When the quake hits, they're automatically shut down and work the way it was supposed to. And then the emergency generators in the basement, that's the bad part, the basement, take over to run the electronics and pumps to keep the reactors cool, so everything's cool, so to speak, until the tsunami hits, because, oh, did we put those generators in the basement? They were actually told to put them on the roof, but some engineer decided not to. So the tsunami comes, the 15 meters of water takes out the generators, and also takes out the connection to the power grid. So now they have no way to get in there and make repairs. They don't have power. All 3 operating reactors go into full meltdown. Hydrogen explosion damages the secondary cladding, or the cladding, the secondary containment in some of the reactors. And despite all that, the total radioactivity was only about 1/10 of that at Chernobyl, which I think is amazing. So here's a picture of the reactor on a beautiful day. Here's the exact same view with the water rushing in. Did I mention the generators were in the basement? Hey, but then there are people who will say, well, you know what, coal's not safe either. Look at all the coal mining accidents. So here's death in just U.S. coal mines in the last 10 years. Here's 2001, 13 people killed. 2006, 12 people killed. 2006, another 5 killed in Kentucky. 2007, 3 miners and 3 rescuers killed. In West Virginia, 29 people killed. So there are people say a lot more people get killed by coal mining. Yes?
Well, and then what about China? That's
Yeah,
like
exactly.
5,000 or 6,000 a year.
Yes, exactly.
Some ridiculous number.
It is. So you can decide about the argument that nuclear is dangerous. Basically, here's a summary. It's hard to estimate the reserves. We have to deal with nuclear waste. It's possibly a very low cost fuel and bang for bucks. Total, lots and lots of energy. Now, I'll remind us again that a week from Wednesday, Dr. Denning from Nuclear Engineering is going to come and talk to us, and this should be fascinating to see what he says. And on this Wednesday, we'll have someone come and talk about the new breakthrough in clean coal, and no class next Monday. Okay? All right? And I'll try to give you some more homework because I know you're bumming you don't have any. All right? The homework 5 was supposed to be due after the spring break, but I saw everyone handed it in. So, okay. I'll make more. Run and play. Okay.